So let's take a look at the torque and force on a dipole in a B field. We're going to start with a current loop in an external B field, and then we'll extrapolate to a dipole. These concepts are very important for looking at the way, for example, molecules and atoms with dipole moments interact with magnetic fields. So we're going to start with this square loop, and it has the side A, so A by A, and it's in a uniform field, and I've drawn the loop such that this is one side of the loop, and then the other three sides are either into the page or parallel to this one down below the page. Here's the uniform magnetic field. Here's the A vector that's perpendicular to the coil. And so if this became a dipole, this might be, for example, the direction of the dipole moment. We're going to use the force equation that we've used before and just look at the magnitude. It's equal to the magnitude of I, and then the integrand is this small vector dl crossed into B. And dl, of course, is an element of displacement along the direction of the current on the wire itself. The fact that B and dl are perpendicular to each other, and we can treat them as constants, then the magnitude of the force simplifies, and we just have the magnitude of the current, the length of one side of the coil, and the B field magnitude. All four arms have the condition that we just mentioned, so this force magnitude is what we have. If we look at the coil, these forces will be in different directions because dl is in a different direction on each side. Now it's kind of hard to see these relationships to get the directions of the force, but I've drawn this here so that the coil parts that are shown here correspond to the parts of the square where the current is going into the board or into the page and then coming out of the page. So we're talking about these parts of the square right here, so this one and this one. If we take a look at this side here, these correspond to these components here, so we might call this one this side right here. If we draw this in a little diagram here where we have the B field going along the direction of the B that we've put up here, and the current vector, which is along the direction of the current, so it's along this wire right here, then if we take I cross B to get the direction of the force, then what we see is that it comes out of the page, and so I've made a little stubby force here. And so up here, this force is coming perpendicular to the current direction. It's pulling the loop in this direction here. Now because I reverses direction, then this force switches to the other direction. So the two forces on the parts of the coil corresponding to this one and the one below cancel each other. We're just stretching the coil, which we're ignoring in terms of the deformation, and so we can say that those cancel. Okay, the other components correspond to these current directions perpendicular to the page, and our current, of course, is still along here. This time, if we take I cross B, we get the forces heading off in these parallel directions, normal, of course, to B, and it will be normal to the current direction, and that'll give us our force. And the same thing for here. So that's what creates the torque. So let's put in the lever arms. The lever arms, this is supposed to be the center of the coil, and the lever arms are just A over 2 for the length of the lever arm. If we want to do the torque, we want to have the component of force perpendicular to the coil, so parallel to the A vector here. And the magnitude of that force will be F sine theta, where theta is defined either here or here. So as you turn the coil, so for example, when the coil is flat along here, then that force will be 0. If we now come to the full 90 degrees, so we're up here, the force is a maximum equaling to the magnitude of the force. If we now put that into the torque equation, we have 2 here because there's one force up and one force down, so they're both contributing to the torque. And then we have the lever arm and then times the magnitude of the force perpendicular to the loop. So the 2's cancel, and we have this expression here. We have AI times AB sine theta, This is 1A, and then remember there's an A in the force. Putting those together then we have AIB, and here is the sine of theta. Realize in terms of a dipole, what we would do is let this quantity here get very small and set the value of this quantity equal to m. And actually what we're saying is that we let A get small and we keep the product constant. That's a better way to say what happens. And so here's the magnitude of m. And then if we go back here, then we have an m times b sine theta. Well, that's just equal to the cross product, and the direction of this cross product indeed is the correct direction for the torque. For this problem right here, if you take b in this direction, m in the direction of a, then that will point out of the page. And so the torque is about this center here out of the page. So let's look at the potential energy of a dipole in a magnetic field. Before that, let's consider a spring with a spring constant K. So we're going to apply a force to stretch the spring, and that will elongate the spring distance x. But the force that's exerted by the spring in return is minus kx. Here's the force to stretch it. So the work done to stretch the spring is force to stretch the spring dx, integrated from 0 to x. If we look at this then, the work done to stretch it is equal to 1/2 kx squared, which you've seen before. The potential energy is the work done to stretch the spring, and so that means the potential energy that you put into the spring is 1/2 kx squared. This is greater or equal to 0, where we've taken arbitrarily the 0 at x equals 0. If we plot that u of x or w of x, then as you stretch the spring, potential energy or the work done goes up in this parabola corresponding to the x squared. Over here we have a mirror image of that, and what does that do? Well, that's equal to the compression effects. As you try to squeeze the spring, you also increase the kinetic energy, but notice the slope is different, and the slope will determine what direction the end of the spring will go if you let go. So this goes towards 0 from negative values of x, and this goes to 0 from positive values of x. The minimum is here at the 0 point here. Now let's look at a magnetic dipole, and so we're talking about the potential energy of a dipole in a uniform field, and this will be determined by the torque. So the maximum potential energy is when the dipole is opposite the field. That's over here. If you twisted the dipole so that the magnetic field is opposing the direction of the field, then you have the maximum value of the potential energy. The minimum is when you come over here and you have these parallel. So how do we get that? Well, you look at the torque equation here, and obviously if these are parallel or anti-parallel, you're going to have the maximum value. The difference is that in this position here, if you just took this arrow and slightly increased or decreased the angle, this thing would want to flip in this direction here. Whereas here, if you displaced it, it would just want to return to the 0 position. So if there's no friction, you tend to see it oscillate about this point. And of course the same is true of the spring, where you would just oscillate back and forth from the 0 position. This shows you how the potential energy changes. So now we have to calculate the potential energy by calculating the work done to twist the dipole. If we take the magnitude of the torque, it'll be mb times sine theta, which is the sine theta, or the theta is the angle through which you twist the dipole. We want the work done to do that twisting, and it's starting at theta equals 0 and going to the angle theta. So come over here and we take the magnitude of the torque and integrate that from 0 to theta d theta. And so putting in the magnitude of the torque, and remember m and b are constant, so we can bring those out. Doing the integral, we get minus mb times the cosine of theta minus 1. Okay, so remember what this is. This is equal to the increase in potential energy generated by the twist to the angle theta, starting from theta equals 0. So just repeating that then, here's the potential energy at angle theta equaling to this quantity right here. If we were to plot that, it looks like this. So here I put minus pi to pi. You'll notice that there's a minimum about the direction in parallel with the magnetic field. And then as you go in this direction here, you can see that it reaches a maximum here at pi. Now if you twisted it the other way, of course, you'd have minus pi for the angle here. We can change the zero of the potential energy as we wish. And so for example, if you take this minus sign and this minus sign, and so you'd have a plus 1 in the overall equation here for this factor, you can just simply drop that. And so you'd end up with minus mb times the cosine theta. In terms of the curve, this is what it did. So here's the old one. Notice this is a 2 here for the units we used. And now it's a 1. And that's simply dropping the 1 that we have over here. Obviously we let these constants both be 1. Restating it, the 0 of u is arbitrary. We often write this as just the m dot b term because n dot b is equal to this function here. And the minus sign takes into account that we have a negative term here in the integral which gave us this minus sign. This is the potential energy, and in a very useful equation in terms of the m and the b. Now let's look at the force on a dipole. And I think we've already discussed that if you have a loop in a uniform magnetic field, then what happens is you get all the forces equal to each other. And so they all cancel out, and so you end up with a net force equal to 0. So restating that, the net force on the loop or magnetic dipole in a uniform field is 0. Well, that brings us then to an inhomogeneous field, and so we'll let tau be a region of space, not torque, with an inhomogeneous B field. And we're going to assume that there's no currents inside this volume, so J is equal to 0. This volume could be small if you wish, so that if you had current out here, it wouldn't matter. M is our dipole moment, and it's oriented along the z-axis just for simplicity, and here's our B in this direction. Before, we just derived this potential energy, and so we give the same equation that we had before. We look at the force on the dipole in terms of this gradient of this potential energy, and of course with the minus sign. Putting that here, we have minus the gradient of minus m dot b, and so that gives us a equation for the force on the dipole equaling to the gradient of this dot product. Remember, this is a scalar. Taking the gradient gives us a vector. Well, this is an important equation as is. You could start here if you wish for finding the force. There's another form I want to develop, and for that we have to use an identity to evaluate the right-hand side. Let's just take arbitrarily A and B. This is not necessarily the B field. And we say that we have the divergence of A dot B. And so then we have this identity we derived earlier using epsilon ijk, that we have these various cross products and dot products here. Let's put in our M and B. So this time this is the magnetic field and A is equal to our dipole moment. So we just substitute. So now we're looking at the force on the dipole in the case of a inhomogeneous field. And what that's going to do is make these terms important. Here we go again. We have the same setup here. We look at the gradient that we just wrote, so this is just repeating that equation. And we're going to look at each term. This is equal to 0 because remember the curl of B is equal to mu0 j. If j is 0, then the curl of B is 0. So we can set this equal to 0. M is a constant, so the curl of M is equal to 0. And so this is equal to 0. The last term is B dot, the del operator operating on M. What this will do is give us differentials of the components of M. And since M is a constant, this will equal 0. If you wish, you can expand this operator, so bx times the partial with respect to x, and so on. And all of those will have partials with respect to a coordinate, and that operating on M, and that'll give us 0. That leaves us with the one term, and that's the del operator operating on M dot B, And because this is a constant, we can move this into a operator that is m dot del operating on B. This will end up being a scalar with partial derivatives here operating on a vector, so we end up with a vector. And so we can rewrite this as F on a dipole is equal to, as we said, minus the gradient of the potential, which is equal to m dot del times B. So that's a second equation which we used by eliminating these terms here. We consider that as equally important as the one that just involved del operating on m dot B. Now we're going to use this to answer a very fundamental question, and that is, why do magnets attract or repel? We know magnets have poles, and the N versus S in terms of the nomenclature for the types of poles is determined by how magnets behave in the Earth's magnetic field. For example, if we had a little dipole magnet here, consider this a bar magnet of small dimensions. We've already said that the torque on the dipole will be equal to this, where B is the field in the vicinity of the dipole. And remember that this will line up so that it's stable in the theta direction, which means that these are parallel to each other. In terms of a compass needle, it'll act as a dipole. It'll orient itself along the direction of the field, and so that's how we say that the compass has this orientation here. So the North Pole on the compass needle is pointing towards the North Pole. Now realize that the way these field lines are generated would be similar to having a big bar magnet inside of the Earth, which of course is not true. But the currents of molten material that have some charge rotating in the Earth give us this kind of magnetic field. Well, this is the same for a bar magnet. If you hang a bar magnet with a string and wait for it to damp out, it will also line up. It's just easier to see it with a compass because the compass has very little rotational inertia, so it lines quickly. If we now put these magnets parallel to each other but close to each other, once the pole designation has been determined, but then we observe experimentally, and I think you did this in grade school, and find that the magnets attract if you have opposite poles near each other, and they repel if you have the same poles. If we take a bar magnet and look at it in terms of the physics of magnetism, what it can be described as is a whole bunch of aligned dipoles. And so here's a dipole here, it's a little current here, and it has a south and a north end. And so if you put a whole bunch of these in here and they align, then you have a bunch of dipoles representing the magnet. Here's the typical B field for a bar magnet. Most of the field lines leave the ends. They're always loops. They come back to the South Pole. Some of them are sneaking out on the sides, do have field here. Similar, by the way, to the Earth. You see you have field lines out here. So every part of the surface tends to see a magnetic field. Again, here's the magnetic dipole field. For both, what you see is that in the vicinity of the end of the bar magnet, in this case, and this end of the dipole, you have an inhomogeneous field. These field lines are going off in different directions. If you were to measure the magnitude, you would expect, for example, the same distance away, that it might be actually different. And that's what we mean by inhomogeneous. This inhomogeneity, for example, this field line here, which is parallel to the axis of symmetry, the field gets weaker and weaker as you go along. So that's another property of inhomogeneity, where you just have a distance dependence, in this case falling off. And we've already done a dipole before. We call this the z direction, that the magnetic field decreases as we go away from the dipole. We're going to treat both the magnets as dipoles of equal strength, m. So we've got two magnets, and we're just going to treat them as the big dipoles. We'll let the axis of symmetry be the z-axis, and we're going to consider the magnetic field due to the left-hand dipole acting on the dipole moment on the right. We'll start with the orientation in the same direction. This dipole here on the left represents a magnet where you have a north here and a south here. This represents the right-hand magnet with the south end here and the north side here. And we'll call Z the distance from the dipole on the left to the dipole on the right. We start with an equation we developed for the B field of a dipole, and that's equal to this prefactor with r to the third power, and then this is the expression in terms of the magnetic dipole moment field point, and then here's the same thing, m left. Okay, now we're going to take z-axis dipoles aligned along the z-axis, and we've already said what z is. The left hand m is at z equals 0. So setting these equal to the magnitudes times unit vectors, m left is the magnitude of the dipole times z hat, r hat is z hat, r is equal to z. What we're doing here is finding the unit vector in this direction here to describe the field due to this dipole here. And we're talking about these r hats right here. And so the distances r equals z. Plugging those in to the field due to the left-hand dipole, we get this expression here. And if we collect terms, we have that the field due to the left-hand dipole is equal to this quantity here times z hat. And z, of course, is the position of the dipole on the right. Okay, now we've developed this equation before, so it should be familiar. Now let's take a look at the dipole on the right, and we're going to take the same magnitude. So it's equal to m times z hat, so it's in the plus z direction. We go into our force equation, which was m dot del operating on B left. So here's the m on the right hand side, and the B is due to the dipole on the left hand side. So here's the force on the m right. Plug that in. We have mz hat dot del operating on our B left. Simplifying this, the gradient is only operating on the function that's in the z hat direction. That's this quantity right here, and it only depends on z. If we carry this out, we basically have the derivative of 1 over z cubed, and so we get minus 3 over z to the fourth. Collecting everything, this is the force on the right hand dipole. This is its magnitude. It's strongly dependent on the distance. And notice, it's in the minus z hat direction. This dipole with these orientations is pulled this way. It's attracted. And that is the prediction of the grade school theorem, which is that if you have north-south, north-south, it will be attracted towards the other magnet. We can right away say that if you turn one of the dipoles around, you're going to simply flip this, and so the force on m right will be in the plus z direction, and therefore it repels. The basic conclusion is then the origin of attraction and repulsion of bar magnets is due to this inhomogeneous B field of one bar magnet, which is the equivalent dipole on the left, acting on the equivalent dipole on the right. The final result then is that you would not have this behavior if you did not have this inhomogeneous B field. So what we've proven here is the grade school experimental observation in terms of magnetic dipoles. So next time we'll start the discussion of magnetic materials, which I think you'll find very interesting, and there are jobs here if you're interested.